Okay, now let's take a look at trigonometry proper. So here's the deal. Right triangles are so pervasive in math and science that actually the ratios of the sides of right triangles are essential. Like they're used often, like a lot. Um, and so at some point, people introduced this idea that, well, what if we like look at those in terms of functions, right? So function, certain input, certain output. So how does that work with trigonometry? Well, you basically have all these different possibilities of ratios to the sides, right? You can do 1 over 2, 1 over root 3, 2 over 1, 2 over root 3, etc. So people said, okay, well, let's look at like 3 of the ratios proper. And what they ended up choosing was the following, okay? And so this is all just by definition saying, hey, if I want to, like, let's just take one example. Let's say I want what we're going to do here is look at an angle. Let's take the example of 30 degrees, okay? I can look at the side opposite to 30, which is the 1 over the hypotenuse, which is 1 over 2, okay? And by the way, in physics, this is used all the time because you decompose forces into different vectors, and like, gravity is always the vector pointing down, just to give you one idea. All right, so people said, well, we got to call it something, so we'll call it the sine of an angle. So this is by definition. But before I put up the individual definitions, I want to show you how to look at it as a whole. It's a little trick to memorize, and there's one other memorization piece. And I learned it via SOHCAHTOA. And how do you write that? Well, here's how I learned it, or how I taught myself, you could say, because I couldn't spell it. Like, how do you spell SOHCAHTOA in terms of all this? So I know so, and I've got the ka, and then toa, I put in h's otherwise. And then the idea is that this is an acronym, and it means the following. The sine of an angle is the opposite over the hypotenuse, okay? That's what the SOH means here. And because once you start doing this stuff, it's sine, cosine, tangent, opposite, adjacent, and you start to be like, well, which is what's what here? It can be confusing. So this is a mnemonic device to try to help you remember it. The cosine of an angle is the adjacent over the hypotenuse. Excuse me. No G adjacent, add adjacent to J. And finally, the tangent is the opposite over the adjacent. Okay, so these become functions in their own right. Now let's look at an example of how this would work in practice. So you might say, what's the sine of 30 degrees? Okay, well, if I look at this picture, what this tells me is that it's the opposite side over the hypotenuse. The side opposite to 30 is 1, okay, because the 30 is made up of these two rays, you could say, segments really, and the only side that's not making up that angle is the 1, so it's the opposite. And the hypotenuse is always this one. It's always the longest, so it's 2. So sine of 30 is 1/2. Okay? We could do some other ones. Let's do all the 30s and see what we get. What about the cosine of 30 degrees? Okay. Now the cosine of 30 says adjacent over the hypotenuse. Now adjacent, right, might not have as clear of a meaning. And so if you look at the 30, in effect, there are two sides that are adjacent to it. Adjacent means next to, the root 3 and the 2. But the 2 in this scenario is always reserved as the hypotenuse. So you're only comparing the 1 or the root 3. And so because 1 is opposite, then root 3 is actually the adjacent. So it's root 3 over 2. And finally, if we look at the tangent of 30, what do we get? Well, I go to tangent, it says opposite over adjacent, so the opposite is 1 and the adjacent still is root 3. Great. Okay. What about the other angle? Let's consider the other angle. Let's consider 60 degrees. Okay, let's do a comparison. So what about the sine of 60 degrees? Okay, try it on your own before I say it. Okay, look at it. Use the definition. Okay, like I'll tell you one thing. It's not the same as the sine of 30 because 60 is in a different position. So even though the 2 is going to be the hypotenuse for all of them, the 1 and the root 3 are going to change. Right, so doing it together, you think about what you think it is first. If I'm looking at 60 as my angle, and I definition is opposite over hypotenuse for sine, opposite of 30 is now this side. It's the root 3. The hypotenuse is still 2. And the cosine of 60 degrees, try that one. Go to the 60, look at the definition. It's the adjacent over the hypotenuse. The side adjacent to 60, I don't want to use 2 because that's hypotenuse, so it's 1. And the side, well, it's the hypotenuse is again 2. Note that the hypotenuse doesn't change. And finally, what's the tangent of 60? Let's do this one together. Opposite over adjacent. I come opposite, I get root 3, and adjacent is 1. So it's root 3 over 1. I'll go ahead and leave it as root 3 over 1, even though that clearly simplifies to root 3. You would usually omit the 1 there. Okay, so what do we just do here? These are basically all by definition. Okay, so the idea is this. You're taking actually an angle as your input, okay? In this case, we have 30 degrees and 60 degrees. The function, they're called sine, cosine, and tangent here. And the output is actually the ratio of two sides of the right triangle. Now, here's something a little bit interesting just to show you. What if I had chosen this triangle instead? Okay, let's just do one of these. Let's look at the sine of 30 degrees using this triangle. Would it be different? Okay, well, let's check. Opposite is 3, and the hypotenuse is 6. So it would be 3 over 6, which is 1/2. That is the power of trigonometry. It doesn't matter which 30, 60, 90 triangle you use. They will all give the sine of 30 degrees equals 1/2. Now, you must learn how to do this without a calculator. Okay? It's just part of the deal when you're at this level of math. These functions are so pervasive in all the math and science you're going to see going forward that you actually want to get to a point where if somebody says, what's the sine of 30? You can just take a moment and say 1/2. You don't want to waste time getting out a calculator to do that. Now, you're not there yet to maybe do it quickly, but you're going to learn some techniques to kind of improve the process to get these answers more quickly. For now, what the approach would be, like if you have a quiz and the teacher says, what's the sine of 30? You want to draw this triangle, actually. So once you know your 30, 60, 90 triangle, and you can put that up, then you can use these definitions, okay? You could literally write that triangle in SOHCAHTOA to deliver the correct answer in the ways that we just used here. And that's kind of the approach for beginners. That's what I want to encourage you to do. Okay, I do want to share with you, though, there is one more right triangle that's really important. And here it is. It's the 45, 45, 90. Now, if I draw those marks like that, by the way, that would indicate that these two sides are the same. They're supposed to be. My picture is a little off there, but I try. And if those two sides are the same, then these base angles are the same here. Okay. And to have the same base angles, again, they've got to add up to 90 because that's 90. Some has to be 180. So they must be 45. Okay. So this is now a 45, 90 triangle. And the question would be, what about the sides? Well, you don't have to memorize this one. It can be worth it, but the reason why I say you don't have to is because remember this little trick where you can pick any side to be 1? Well, the natural side to pick to be 1 would be which one? I mean, you could pick either, but I like to start with 1 as the smallest side. So that would be these two sides. And now I can actually use the Pythagorean theorem to get the third side, C. Because I get 1 squared plus 1 squared equals C squared. 1 plus 1 is 2. I get 2 equals C squared. Excuse me. And then C would equal the square root of 2. Okay? So this is root 2. Right? So there, I didn't, quote, memorize it. I was able to figure it out using the Pythagorean theorem. So if you're a minimalist when it comes to memorization, definitely memorize this triangle. memorize SOHCAHTOA in terms of like, you've got to know just like which ratio is the sine. I mean, you have to know those. And so again, that's a device to try to remember really what's underneath it is the key here, right? What you'll find is that you can learn what's underneath it by just memorizing the phrase above. And you may or may not memorize this one. The point though is this: if you are given, okay, something like, say, the cosine of 45 degrees, you've got to be able to get the correct answer without a calculator. Well, okay, let's try that, right? What have we learned? We've learned that the cosine is the adjacent over the hypotenuse. So for cosine of 45, what's cool is I could pick either angle here. So I'll pick this one. The adjacent is 1, and the hypotenuse is square root of 2. So it's 1 over root 2. Cool. And this is kind of nice too. The tangent of 45 is what? Well, the 45 degrees here, tangent's opposite over adjacent. It's not the hypotenuse. It's 1 over 1, which is 1. So that's really special. Tangent of 45 degrees is 1. Okay. Tempted to go on a side note about this leading to the first derivation in human history of pi as an equality. But that requires infinite series. It's just one example of how tangents and these functions are like really important. I'll give you one other little just heads up in the future. When you graph these, which we'll do at some point, they actually make waves, actual waves. Like the sine of x is a wave. It's kind of cool. And every wave, like real waves, like talking about water waves, electromagnetic waves, and electromagnetic waves are everywhere because light's an electromagnetic wave. Your phone's using electromagnetic waves, cell phone to communicate with people through towers, microwaves, gamma rays, radio waves, X-rays. Those are all electromagnetic waves. They're all modeled using sine, the sine function. You can also use cosine too. So these are big players here, right? So it's kind of exciting actually because it's something new that you're going to get to use. And what I'm presenting here are kind of the fundamentals of what you're expected to know. And I will say this too, well, maybe I'll break it out into a little separate video, which is what the calculator and the simplification of square roots, because you're going to need to be able to navigate those in order to do this stuff. But let me conclude this video with a simple example problem. And it could be something like this. It's like a little application of how you can use what we just did to figure out something different, like possibly the area of a triangle. So imagine you have a triangle that looks like this. Let's say you have, here's a triangle and got this right triangle here. And now, what might you know about this triangle? Well, let's say that these are both 45. Okay. So you've got, right, so this is a straight line, so there's also a right triangle. And maybe you know that you'd want to know the whole base here. So let's say that the base of the, well, how about this? Let's split up into two sides. We'll say that this x1 equals 5 and x2 equals 7. Okay? And the question would be, what's the area of this triangle? Well, actually, you could do this just using straight geometry, because you can solve that. The 45 is nice. If you know one of the sides, right, this is 45, that's 45, then you know that this is also 5. And so for the area here, it would be 1/2 base times height. And so the area would be 1/2 5 times 12. And so that would be 30. Okay. I didn't put units in, but if it was like meters, you'd want to say it's meters squared. Okay. So that's like one example. And I guess, you know, let me make it just maybe a little more challenging, right? So we'll do one more. Because now you don't really have to use, quote, the trig, but let's do one where you got to do maybe a little more work. And how about this? And start with, say, the 30, 60, 90. Actually, I like to do it here. So now I know this is 30. Maybe just go a little bit more, okay. And imagine that's all one straight line at the bottom. It looks a little broken. And we want to figure out, I don't know, like we know maybe the whole side has a base of, I don't know, 10. Maybe this side is 8 or something. Okay. We're going to figure out what's the area of this triangle. So this is a hard problem, really hard if you don't know your 30, 60, 90 triangle. But if you know the 30, 60, 90 triangle, which I just erased, you can solve this directly. And so the idea is, right, so you know that the whole base is 10, but you don't know the height. But if you can get the height, you have it. But look, this is a 30, 60, 90 triangle. And so it's right, so this is 60. And if you remember what I just shared with you about the ratio between these two sides, say h and the height, and this 8, then you would get that h is half of the hypotenuse, which is 4. So the area is 1/2 base times height again, but in this case, now it's 1/2 base is 10, height is 4, so it's 20. Okay? And these are just some basic applications that you can use for solving areas of triangles, and there are much more important ones. Let me just wrap. I know I keep saying I'm going to wrap this, but you know, very, very big one here would be like the area of a hexagon. Because how do you get the area of a hexagon? Right? I mean, this doesn't fit like a lot of like kind of the basic, oh, clearly the formula is this. Maybe some of you know it, maybe some of you don't. Well, one way, if you take the point in the middle, this is a regular hexagon, and you make a triangle. So based on construction, the idea would be that, you know, this splits into 6 triangles that are all the same, assuming it's been drawn properly, and you can actually figure out the area of one of them and multiply it by 6 for the whole one. Well, how are you going to get that? First of all, you got to have some measurement, right? So let's say that the side is 1. Okay, what's the next step? There's a formula for the sum of the angles of a polygon, but you can actually get it from this diagram. So if you have 1, 2, 3, 4, 5, 6 triangles, you have 6 times 180 degrees, but you eliminate from that the circle in the middle, because that's 360 degrees. It's not part of the angles, okay? And so what you end up with is that the angle is basically equal, let me write it out for you. So 180 times 6 minus 360. That's also like 4 180s, okay? Why is it 4 180s? Because you're taking off 2 of the 180s here. And so that's the formula most people remember, is it's basically n minus 2 times 180. And so if you know that the sum of the angles is 720, then each of the 6 is 120. These split them in half, and these are 60. Okay? But if that's 60, to get the area of this triangle, what do you need? You actually need the height. And if this is 1, okay, the whole thing is 1. This side is 1/2. That's opposite to 30. The height is actually 1/2 times the square root of 3. Okay, let's put that up here. H equals 1/2 root of 3. And so now I can get the total area of this thing, because the area, let me just write the area of the triangle, is now 1/2. The base is actually the whole thing, the 1, but now the height is 1/2 times the square root of 3. You can write this 1/2 times root 3. And that's just root 3 over 4. Okay, so that's one of those triangles times 6 gives you the whole thing. That's an advanced application. You don't actually have to know that right now, but I'm just trying to give you an idea of the power of this stuff and where it's going.